Hey everybody. We're going to go ahead and go through some of water's unique properties. We're going to talk about what causes these things, what some of the specific properties are, and then kind of close up with what does that mean for us going forward, and kind of how does that tie to our Flint water crisis. So first thing, there were two specific types of covalent bonds. Hopefully everybody found these. Remember, a covalent bond is anytime two nonmetals bond together. So obviously in water, hydrogen and oxygen bond together. This involves, again, a sharing of their electrons. There are two ways that they could share. You can share obviously evenly with each other, or sometimes they'll share unevenly with each other. If they share evenly with each other, as the picture shows you there, this is called a non-polar bond. You know, each of the two hydrogens pulls evenly on the electrons that they're sharing with each other, and therefore it is not polar. If, however, they are shared unevenly, they do call this a polar bond. So you would see in this little diagram, chlorine is being kind of evil and pulling way harder on the electron than poor hydrogen can. So what this is going to do then is create kind of a charge around chlorine. Now it's not an ionic charge. Chlorine hasn't pulled the electron completely out of poor hydrogen yet, but it's pretty much spent most of the time around chlorine, which is going to make it pick up kind of a partial or slight negative charge. What this means then is that because these charges may be uneven, it leads to specific attractions between different molecules. Forces that hold together molecules to other separate molecules are specifically called intermolecular forces. Inter meaning between, and then obviously force would be some sort of an attraction between them. There are three main types. You really only need to know one of them. Dispersion forces are just simply, hey, these things, electrons are close to each other, great, there's a little bit of an attraction. We're not going to do anything with those. They're not that important. Dipole attractions, basically, again, because of the polar bonding, you've got one end being slightly positive, the other one slightly negative. There's a little bit of an attraction there. The one that we're concerned with, because we're dealing with water specifically, is hydrogen bonding. Hydrogen bonding, then, because this is such an uneven sharing, it's almost to a point where it's completely spending all of the time around oxygen. Then because poor hydrogen doesn't get the electron very much, it picks up this partial positive, oxygen's partially negative, and then you have this pretty strong attraction holding it together. So what are the effects of this hydrogen bonding on water, and what properties does that give water, and why is water such a big thing? Well, first thing that's a really big thing for us is that this makes water liquid at room temperature. Almost any other state substance that has um, the same size or the same mass is almost always either a gas or a liquid that's a very, very volatile at room temperature. Do remember, obviously, water that can exist in all three states of matter on Earth, but around room temperature, water's a liquid. So again, compared to things that are about the same size, water is the only one that's a liquid. Methane's about the same size. It's a gas. It melts at 183 degrees below 0 Celsius. Ammonia is roughly the same size. It's negative 78 degrees Celsius. Nitrogen is bigger, and it's negative 210 degrees Celsius. And then you've got water that's around zero for its, again, melting point, and it's definitely a liquid at room temperature because of that strong attraction between the hydrogen and oxygen on different water molecules. The shape of a water molecule, when you're drawing these things, and we are going to ask you to draw them later, make sure you understand that it is not in a straight line, but it has a bent shape. And the reason for that are the lone pairs of electrons that are on oxygen. The angle is 109 degrees. It's not that important. Just remember again that it is a bent shape. It's not 180 degrees. It's not in a straight line. What this again allows is those attractions to occur, and again, make water likely to be a liquid and likely to have a bunch of other properties that we'll talk about here in a second. So if we were to ask you to draw water, you can see again this little bent shape. The hydrogen's just a little bit below, kind of looks a little bit kind of like Mickey Mouse, where you've got the little ears, and then you've got oxygen, and then the attraction again between oxygen to hydrogen is your hydrogen bond. These little dashed or dotted lines here are telling you hydrogen bonding is occurring. And I had to have one, you know me. So what evidence do we have? Well, hopefully in the lab that you found, water forms droplets. It does not spread out. It has high surface tension. It beads together quite easily. So you can see the little droplets forming. What it does, or how that shows us this, basically is it means they all stick together very well. They don't want to spread out. They don't want to repel each other or get away from each other. They want to stick together. Water can stick to itself. That's called cohesion. Water can also stick to other things. That is called adhesion. So in the little diagram here, the two water molecules stick to each other. You're talking cohesion. Water sticks to something else. Then we're talking about its adhesive ability, or its ability to undergo adhesion. One of the other tests that we ran, capillary action, remember, forms up or climbs up tubes, forms a meniscus, all those things. Basically, again, does this because of water's ability to stick to other things and then stick to itself. As it climbs the tube, because it's sticking to the glass, it also is sticking to itself and pulling up other water molecules along the way. So you can see again the adhesion on the sides to the glass and the cohesion to other water molecules beside it. So you get this kind of a meniscus, or again, capillary action rising up a little capillary tube like we saw in the lab. Remember again, water would have a very high surface tension. This is again due to that hydrogen bonding. Pretty much any of the properties that we'll talk about, this is why it has all of these things, is hydrogen bonding. So you can kind of see again, these little water molecules all have an attraction to each other. So they form this little droplet or bead. Again, high surface tension. Please don't be the person that thinks this could actually happen and drops your phone into a glass of water. Water also has, because of all these attractions, has the ability to absorb a lot of energy without changing its temperature. If you put a lot of energy into water, they have the attraction to kind of hold themselves in place. And while they may vibrate and move a little bit quicker, they don't necessarily change the temperature all that much because of those attractions that are close to it. Remember from the activity we did a while ago with the metal and the wood and the plastic, metals have very low specific heats. They change their temperature quite rapidly. Because the water has such a high specific heat, it allows to keep the planet at a relatively constant temperature. Again, you're going to have temperature swings based on all sorts of other conditions, but we do keep a relatively consistent or constant temperature. Thinking about again where the most radical temperature changes take place, they take place mostly in the desert because there's little to no water to absorb and redistribute that heat. In Iowa, we don't tend to have really, really rapid temperature changes. Our temperature change over the course of a day is about 20, 30 degrees. Desert, those things can swing from 110 to 120 to almost below freezing at night. You're talking about a temperature swing almost 100 degrees. You can kind of see by the diagram here, again, this is what allows places like anywhere around a coast or on a beach to keep a pretty consistent temperature. Water, again, would absorb that energy, and at night, it would release it. The heat would blow in to keep it nice and consistent. As it cools, it'll go back out, and then it would just reverse when it warms up during the day. What's so special about ice? Well, believe it or not, ice should actually sink in water. Most solids should sink. Solids are more dense than their liquids, but ice doesn't. Ice floats, and we all know that. We've seen it in our cups and all sorts of things. The other weird thing with ice is, and you've probably seen this if you've ever made the mistake of leaving a sealed can of pop or a bottle of pop in your car overnight when it got really cold and it exploded on you, or this is the same reason that people, when they leave for the winter, if they're snowbirds and go to Arizona or Florida or wherever, that they'll drain their pipes to make sure that the pipes don't burst, because as ice freezes, it actually expands into a crystal that makes it less dense. And again, we've all seen ice float on water before, but it's just that's a weird property. It's not actually supposed to do that. It does that again because of hydrogen bonding and the way that they form these ice crystals. If you look, your oxygen end, your hydrogen end, it creates these kind of big open spaces in the solid that actually makes it less dense than its liquid. If you have the liquid, when they form, they can kind of twist and get into those spaces and makes it actually a little bit more dense than the solid is. All right, so the rest of the time for today, what I want you to do is work on your lab CER. Remember, the question should be written for you on Classroom, and it should hopefully be up on the board as well for you. If you don't get that finished, it's fine. We'll talk about it tomorrow if you need to. Otherwise, make sure that you got all the notes taken. If you need to go back and watch the video again, you're welcome to. And then the link to that PowerPoint should also be posted for you on Google Classroom. And hopefully I'll see you guys on Friday.